we go. Good morning, everyone. Welcome to our 10 o'clock briefing today, Teaching Machine Learning to Get Better Answers. I'm very excited about this briefing myself. I'd like to welcome our three excellent speakers and introduce them. They are Hal Stern, the Chancellor's Professor of Statistics at the University of California, Irvine, and the Director of the UC Irvine Data Science Institute. Genevera Allen, Associate Professor of Statistics, Computer Science, and Electrical and Computer Engineering at Rice University, Director of the Rice Center for Transforming Data to Knowledge, and an investigator at the Neurological Research Institute at Baylor College of Medicine. And David Blei, Professor of Statistics and Computer Science at Columbia University. So we'll get started, and we will have a hard stop at 10:45. So without further ado, Hal.
Thanks, Megan. Thank you all for coming this morning. I wanted to start by mentioning that I organized a symposium on statistics and machine learning with applications to computer vision and genomics, among other topics that will be discussed. And that's 3:30 this afternoon in one of the Washington ballrooms in this hotel. And in addition to Genevera and David, Kevin Murphy from Google will be there talking about some of his work in computer vision and other applications. And he couldn't be here this morning, but he's available then to answer questions as well. My purpose in organizing the symposium and what leads to this briefing is that there's a wide range of approaches to exploring large data sets to advance science. Increases in data sets across the entire landscape, astronomy, medicine, various areas of biology and engineering are getting larger and larger data sets. And there are a lot of different labels that are being attached. So there are statistical approaches, there's machine learning approaches, artificial intelligence seems to be an especially popular topic and label these days. And I guess one of the points that I'd like to emphasize is I view all of these as kind of a wide range of quantitative tools to help scientists make the most sense of their data. And I don't find the labels all that helpful. I was in a talk this morning in which someone said we used machine learning to do task X, in this case to identify bots on Twitter. And to me it matters a great deal what type of machine learning. So I think of methods as varying along at least three dimensions, one of which is how much human input was required to build that quantitative method. The second of which is how much data was required to train and teach that method to do what it was going to do. And the third is how strong the assumptions are and how easy those assumptions are to check for the method. And so if a deep network is used, it requires a lot of data, not much human input, and make certain assumptions about the fact that the population you're applying to will stay the same over time. And so that's a key theme for me. It's not a unique view to me. It's appeared in a lot of places. There was an article in JAMA, the Journal of the American Medical Association, which laid out a very similar argument in that context. That is the distinction between what clinicians do, what an expert system might do, and what the promise of large databases of electronic health records might do as being along a continuum here. And so the presentations that, as I said, we'll be hearing more about this afternoon include emphases in sciences with large amounts of data that feature the potential to learn from large amounts of data and also some of the challenges and pitfalls. And so my main points are to not favor a particular class of techniques, that it's crucial that quantitative scientists, by which I mean statisticians, mathematicians, computer scientists, work closely with domain scientists to figure out for a particular question what data is available, what is the question, most importantly, framing a good question, what data is available, how much knowledge is available to address the scientific questions, and that will lead one naturally to use one of the methods within the class that we're talking about. So I'll stop there and turn it over to Genevera.
Hi. So first of all, thank you very much to Hal for organizing this and Megan for having us. So I'd like to ask today, can we trust discoveries that are made from data? Specifically, there's huge amounts of data being generated across tons of fields of science, from biomedical data to astronomy to climate science and so forth. And machine learning techniques, the data is so large, machine learning and statistics techniques are needed to mine this data to make scientific discoveries that advance science. The question is, can we really trust some of those discoveries that are being made? So let's back up for a second. In machine learning, there's been a lot of emphasis placed on building predictive models. And we have well-established ways of validating when a predictive model is accurate. We can easily test it on future data and see if it makes accurate predictions. For data-driven discoveries, this is much, much harder to do. So data-driven discoveries are things like finding important features associated with a particular outcome in a data set, understanding relationships between features or entities in data sets, finding groups, finding patterns that somehow lead and advance science. The challenge is these are very hard to verify and on given data sets. So I'm going to use a particular example that comes from some of my own work in precision medicine. So in precision medicine, often the goal is to find subgroups of patients with genomically similar profiles so that they can develop common drugs for those patients based on their genomic profiles. The way that these subgroups of patients are discovered is often by taking huge cohorts of clinical genomics data and clustering or finding groups of these patients that have similar profiles. The challenge here is that there's been some cancer types where there's well-validated subtypes and profiles, but for many cancer types and many other complex disease types as well, people have applied clustering techniques to these data sets and it turns out that the subtypes that were discovered have not necessarily been reproducible on additional cohorts in the future. And this has happened time and time again of many different papers published in finding subtypes for precision medicine. Why has this been happening? I would argue this has been happening because the machine learning tools that scientists are using to mine these really big scientific data sets are machine learning tools that are always built to give an answer, to make a discovery. For example, if you tell a clustering algorithm, find groups in my data set, it comes back and it says, I found some groups. And if you tell it to find 3 groups, it finds 3 groups. If you tell it to find 4 groups, it finds 4 groups. How do we know whether those groups are really there and are true discoveries or just an artifact of that particular cohort of patients that was studied? So the question is, how can we trust some of these data-driven discoveries made using machine learning techniques in science? I would argue that the answer is, unfortunately, in many situations, no. But there's some good news because there are a lot of techniques that we can use and many open research areas in statistics and machine learning to try to address this question and say, develop better techniques that not only reports, hey, I found groups in my data, I found clusters, but also report the uncertainty in the groupings that they find and report kind of the confidence in those discoveries that were made. So the next generation of machine learning and statistics techniques that come out need to not only be able to make discoveries from big data sets, which is what we currently have now, but to make discoveries and report how likely those discoveries are to be true discoveries and hence reproducible on future data sets. I'm going to be talking about some specific research directions along these lines, new research directions on making data-driven discoveries reproducible and reporting uncertainty this afternoon in the symposium.
I have to hold it down. Hi. Thanks very much to Hal and Megan for arranging this. Thank you for spending time with us this morning. I'm Dave Blei from Columbia. And I prepared some remarks that really build on Genevera's remarks, citing the same problem, and then maybe giving an overview of the kind of hint at a solution that I plan to describe in more detail this afternoon. So what I plan to talk about this afternoon is my lab's work in the field of causal inference. And as Genevera articulately told us, many classical applications of machine learning, but really I should say many modern applications of machine learning and statistics, are all about prediction. And by prediction, what we mean is passive prediction. given the data that I've seen, maybe it's labeled pictures, maybe it's people watching movies on Netflix, maybe it's measurements of the universe from big telescopes, all these data, what do a machine learning or statistics method can tell me, what do I expect to see next? If the process unfolds in its natural way, what will I see next? That's passive prediction. Causal, what movie will somebody watch next? What image am I going to see next, and what will its label be? Causal inference is fundamentally different. It's about intervention. If I change something about the world, then what do I expect will happen? That's the field of causal inference. And this small linguistic change, just going from the passive voice to the active voice, has real mathematical consequences when it comes to how we analyze data, how we think about what discoveries we can make from data. Thinking passively versus thinking actively lead to different methodologies. And causal inference, actively trying to predict under an intervention, is more difficult, requires more assumptions, but ultimately provides more powerful predictions. And it's not, as you mentioned, it's not what we're doing right now. So we're still in the early days of making causal inference useful, but it's crucial to many aspects of solving problems with data. So for example, I won't talk about the mathematical details of how to do it here, but some of the effects of the causal effects of doing good causal inference are that we can do things like build robust machine learning methods that can handle changes when the world which they're predicting from changes. We can help build fair algorithms. So there's a lot of work in algorithmic fairness around taking legal notions of fairness, turning them, quantifying them in terms of causal inference quantities, and then using methods from causal inference to validate the fairness of various algorithms that are deployed. And of course, the reason we're here to use machine learning to do science, to really understand the world, to understand the mechanisms that are driving the world through the data, we need these kinds of interventional predictions. So that's what I'll talk about this afternoon. Thanks.
Thank you so much. We will now open the floor to questions. I believe we have a microphone in the back. If you could state your name and affiliation before your question. We'll start here. Thank you.
Yeah, thank you. Hi, my name is Benny Mols, science journalist from the Netherlands, specialized in AI and robotics. I was wondering whether you can combine the new approach to AI, like machine learning, with the old approach, knowledge representation, models. I've been to a couple of AI conferences, and I see that these fields are coming a bit together. Could that be a solution to part of the problems that you have described?
I'll start, and then others can jump in, of course. It's a very good question, and one of the things that's challenging in this particular area of research is the names and labels change. So what was artificial intelligence 10 years ago is not what artificial intelligence is now, although the goal has remained the same. So I think the modern attempts at artificial intelligence are typically building on kind of graphical models, that is relationships among kind of a node representation of a problem in terms of graphs and nodes, which is some of the older version of artificial intelligence. So I think they are merging in that respect.
Yeah, the old joke about AI was that when AI has all these problems that are under the umbrella of AI, and once they're solved, they become part of mainstream computer science, and they're no longer AI. So, computer science is filled with a graveyard of AI problems that we solved. And I agree with Hal that as fields like graphical models and unsupervised learning become more developed, we are seeing a merging of these knowledge representation-based approaches to solving problems with data with the more statistically grounded approaches. And that has to do with computation getting better, but also with the methods becoming more sophisticated. It's still a very interesting open problem, and another motivation for solving that problem is that there's more emphasis, more important that we find interpretable methods of AI, that we don't just build black boxes that take in features and spit out decisions. That's very dangerous, especially when algorithms are being used to make important decisions that affect millions of people, or when algorithms are being used to make tiny decisions but for millions of people. Knowledge representation-based approaches to machine learning are, by definition, interpretable and explainable. That's the whole goal. So combining these two ideas is a very important area to work on.
Yeah, no, and what David said is important, and what Genevera and David both said is the importance of the more modern twist to the knowledge representation work is the accounting for uncertainty and the use of probability as the language for doing that.
It looks like that for many applications, you don't need only data, you also need models.
I think that's part of the part of the discussion now is there's a range of techniques, and I think I don't want to speak for others, but there's a robustness that comes from in putting in domain knowledge. At the same time, there is success in some purely predictive settings like computer vision with algorithms that don't have that structure put in, which is learned from large volumes of labeled data, for example. So it depends, again, on the scientific context.
I think you're 100% right that somehow blending domain knowledge with letting the data speak is the way forward.
Tom Keenan from Business Edge in Canada. We had a remarkable case where through doing Google searches, people were able to uncover the names of legally protected, for example, young offenders in cases. And when it was taken to Google in Canada, they said, well, that's because people did this, and we can't really explain how that happened. So I'd like each of you to talk about how well algorithms can explain what they do.
I'll start. We're just very courteous is the issue. It's not that we don't want to answer the questions. It's a great question. That question itself is a very, very active area of research. That is, once I've developed an algorithm to do task A, how do I explain what it does? And there are a variety of reasons we want to do that, just to be able to understand what our methods are doing, to intervene if necessary along the lines that David talked about, but also to make sure one of the applications that is interesting to me is these types of techniques are being used to assist with making decisions about bail or whether to let people out on their own recognizance, things like that. There are certain factors that we don't want to use explicitly in that, but we also want to find out if they're being used implicitly as well. And so there are techniques coming out of some of the computer science departments that I've seen in which people take trained networks and then try to come up with similar, easy to explain rules that reproduce the decisions of the networks. It does not mean that that is what the network did, but it may help with the interpretation. I don't know if you want to add, Genevera.
Yeah, I'll jump in and say there has been a lot of great research in this area. Another direction is people are developing tools that from the get-go are interpretable instead of just kind of black box tools. But I would still caution that with interpretability, you can think of like interpretability of a model as some type of like discovery from a large cohort of data. And I would still say that we need to have some understanding of, is this the interpretation of these models, or is this a interpretation, and some uncertainty in those interpretation of the models, which I think is critically important and a new area of research.
There's not much to add, but I wanted to highlight two aspects. One, of course, interpretability is very important when algorithms are deployed across society because we need accountability and we need to know why an algorithm is doing what it's doing. And two, for science. If we're going to use data to discover something about the world, there's no discovery without explaining and understanding what's going on. And again, the blend, I think that these black box methods, and when we say black box methods, we often mean things like deep learning and neural networks at large scale. They're very powerful predictors. There is a new open area of research, something I work on as well, around how to interrogate the fitted black box method to understand why it's forming the predictions that it's forming, almost somehow separating the prediction problem from the interpreting the predictor problem.
Question here.
Ron Winslow, freelance. I'm a neophyte to this area, so I'm going to ask a very basic question. You've used the term machine learning, you've used artificial intelligence, you've used deep neural networks, and so are these somewhat interchangeable? Are there differences that are important for us to consider in how we use them?
It's a wonderful question. In fact, it's the question that motivated kind of my attempt to set up a symposium this year, because I think it's a question that's on many people's minds. So thank you for asking it. I'm not sure there is an answer, but I'll give my answer. There are a wide variety of methods that people use, and it's not always clear what they mean. So the machine learning is a little bit of a catch-all these days for methods that tend to use probabilistic statistical tools with large data sets. But it really varies quite a bit from fairly traditional statistical methods, names that may not mean much, but just ordinary logistic regression or regression techniques, which come up very early in a student's academic career. They learn those tools. They count as machine learning. But on the other end are some of the purely predictive, more black boxy things that David just mentioned, the deep neural networks, for example. And so lots of things fall under the umbrella of, to my mind, statistics, machine learning, artificial intelligence. So deep learning is clearly kind of underneath them as one example of a type of method. The boundaries between those top-level categories of statistics, machine learning, and artificial intelligence are a lot less clear to me. So I think of techniques as in terms of their features themselves or their characteristics. We use features to talk about what the methods find out about the data, but I think the methods themselves have features in terms of the amount of data they require to be effective, or the amount of human input they require, domain knowledge they require, and things like that. And so that's the way that I like to try and mark up the space, rather than say I used a statistics technique or I used an artificial intelligence technique.
The conventional wisdom is that if you're at a job interview, you should say that you do artificial intelligence, but that when you're on the job, you should do machine learning and statistics.
I can't top that answer, so.
Question over here.
Hi, I'm Alok Char from The Economist. I've got just a couple of questions for David and Genevera about your examples. So you really quickly went over some examples, and I'd just like you to go over them in a bit more detail, because I think they're really interesting. So your one, Genevera, about the cancer diagnostics and the sort of the clustering. If you can just explain what was wrong with the, I understood the first part of it about how you find clusters and so on, but then what the problems are, I'd really like to know. And in your example, David, what are the ways that you can use causal inference to make a fairer algorithm? Could you give me just a few examples that are really concrete?
Sure. So the example I was talking about was using large cohorts of genomics data to find subgroups of patients for precision medicine. And again, this is really important to basically identify patients that have similar genomic profiles. This is used a lot in cancer to say a very famous example is breast cancer subtypes, which has now been very widely validated. This was actually a discovery made from a large cohort of genomic data using clustering techniques and grouping techniques that was later validated in lab science many times. So the challenge with this, and so finding these kind of genomically similar patients so that you can deliver kind of specific therapies based on their genome is kind of one of the holy grails of precision medicine. But it's incredibly challenging to do because with clustering techniques, again, if you have one cohort of patients from one hospital system and you apply clustering techniques on that data set, it might find, say, 5 groups of genomically similar patients in that data set. Another cohort from another hospital system might find only 3 groups of patients. And the challenge is this has actually happened over and over again in the literature. If you look at particular diseases, and I'm actually going to illustrate an example from colorectal cancer in my talk this afternoon, where multiple papers said, we've discovered subtypes from colorectal cancer. But if you look at each of those discovered subtypes, they don't really overlap. Some papers found up to 7 different groups. Other papers only found 3 groups. And most of the patients' profiles never actually overlapped. So what's really going on here is that, again, these machine learning algorithms are always going to say, we found groups or we made a discovery from the data without being informative about, hey, I really think these groups of patients are really, really grouped similarly together, and this is an important genomic profile, but these others over here, I'm less certain about. And so I think that's what we want from kind of the future of machine learning techniques, is that they not only make discoveries, but they then communicate how certain they are in those discoveries. Does that answer your question?
As to your question about fairness, so it's a pretty thorny subject, as you can imagine. To be very clear, what is fair and what is not fair is not something that computer scientists and statisticians get to decide. That's something that's argued about by policymakers and politicians and philosophers and political scientists and others. I brought it up in the context of causal inference for the following reason. So let's imagine that we decide to use an algorithm to make some kind of sensitive decision. For example, I'm a college professor, so admissions into college. We're going to use an algorithm that ingests college applications and spits out a decision about who should get in and who shouldn't get in. And what data do we have for that? Well, we have the last however many years, 100 years of our particular college's admissions committee's decisions. We have the applications, and we have whether or not the students got in. And so the knee-jerk machine learning solution to this problem is to simply fit a deep neural network to that data, and then now you have a black box that ingests an application and spits out a decision. Okay, so the question, of course, is it fair? And the first thing to know is that suppose that admissions committee was not fair. And maybe that's because our idea of fairness changed over the years, or maybe it's because they were a bad committee and they were not fair for 100 years. The machine learning algorithm spits out what you put in. So it's going to then produce a decision-making machine that is not fair in exactly the same way that the admissions committee was not fair. What can we do? Well, there's two stages. One stage is to try to understand if that black box you produced is fair. And where causal inference comes in is to help us make mathematical the notion of fairness. So as an example, there's a legal notion of equal opportunities. And one way to formalize equal opportunities inside there's a way to formalize equal opportunities inside the world of causal inference, to think of it as a kind of counterfactual. Had my race or gender been different, would I have gotten into this college with this black box predictor, for example? And that itself is a thorny thing that comes with many assumptions, and computer scientists and politicians and policymakers can argue and question those assumptions rightfully. But subject to those assumptions, one can define fairness in that kind of quantitative causal way. Then you can ask, okay, with this black box predictor that I formed, is it fair in the sense of, does it satisfy the criterion that I developed based on this causal inference quantification of what it means to satisfy equal opportunities? I know I'm creating a maze of words here, but so question one is, if I quantify fairness, which is thorny, does my black box predictor satisfy my criterion for fairness? Question two is, let's say it doesn't. I think it's safe to assume that if we look at 100 years of admissions committees, we would find some ugly practices. What can we do? Can I take a black box predictor fit to this 100 years of admissions committees, and can I glean wisdom from them, but correct for the ways that they were fair or unfair? So those are the two challenges to using causal inference in the context of fairness. Perhaps a longer answer than you wanted, but that's the idea. And this is brand new stuff. This is now at the cutting edge of computer science research. It's not implemented anywhere, I don't think, but researchers are writing papers about these ideas right now. How do we quantify fairness? How do we build predictors that are fair, et cetera?
Question here. The mic is coming. Yeah.
Thank you. Clive Cookson from the Financial Times. People, again, I'm fairly new to this field. People traditionally give the probability of something being a valid result rather than chance in terms of a p-value. Is that applicable at all to the sort of thing you've been talking about, Genevera? I mean, you didn't mention that. I mean, and presumably if there must be some way of working out whether these 3 or 7 groups have come up by chance because the algorithm's been told to find them, or whether there's some valid genomic reason or biological reason.
Thanks very much. I love your question. I almost feel like it was planted. I was ready to answer it. So the question was about p-values and kind of traditional classical statistical inferential techniques, and can we use p-values and confidence intervals from classical statistics to address whether the results of machine learning techniques are truly there or not. There has been some recent research in this area, but the answer is it's pretty hard. It's very challenging to do, and it can only be done in certain situations. And the reason is that machine learning models, the way they're built, they search over a vast kind of, it's not, when we say a machine learning model, it's not one model, it's actually a vast array of models that they're searching over the data to find the particular groups that it found. And in doing so, all of the assumptions of classical statistics, meaning that you have a nice random variable and a null distribution that follows a particular distribution, they're suddenly all violated because the results from machine learning techniques are no longer following classical statistical distributions. So this is an active area of research in statistics called post-selection inference or selective inference. And the idea in this situation is machine learning models which search over, again, I say a model, but they're actually searching over vast arrays of possibilities for their models to find the discovery from the data. After they've searched over this vast array of possibilities for these models, again, if you think about clustering and finding 3 groups, think of all the possible permutations of how you could arrange a data set into 3 groups. That's a concrete example of the types of models that are being searched over to decide a clustering result. So there are some new techniques that say account for the fact that you've searched over all these possible models. Can you mathematically derive the null distribution and do kind of classical statistical inference after doing machine learning? And there has been some success in this area for a particular technique, feature selection in the lasso. There hasn't gone much beyond that. I'm going to talk in this afternoon about some of my own work on doing these types of techniques for clustering. So for example, after you get these clusters, saying, can we put a confidence region on the cluster centroids to actually see whether the 2 clusters are separate or not. So there are some techniques in this area. It's a brand new area of research. I think it's a very exciting area of research and could really move the field forward.
Yeah, I would just add one thing, if I might, which is that it's important to remember or recognize that the p-value, which has gotten a lot of attention and a lot of criticism over time, it does one thing very well, which is if you have a priori specified hypothesis and a single data set on which you want to test that hypothesis, you can to build a procedure that has certain desirable characteristics in terms of controlling error rates, wrong decisions, and the p-value, it hits that exactly right. And as data sets have grown and the questions and the technologies that you've heard about, the ability to work with the data have grown, the p-value is very limited in its ability to address these new types of questions.
I was wondering if I could ask, oh, there is a question in the back right there in orange, okay.
Daniel Marino from Boston University. A question for David here. with the black box DNN type stuff that is sort of bringing to light the inherent biases in a data set, is there any thought or interest or ability to retroactively detect biases using a black box that would, if infinitely replicated, multiply biases?
Can you say the last part of your question again?
I guess if there
understood
was
the
a,
first.
if there was a bias in a data set, which would come from a bias in actions or collection of some sort, and you used a black box DNN to come to the same sorts of conclusions by training it on that data set, is there an ability or desire to use deep neural networks to elucidate subtle biases in previous systems?
Oh, I see. Yeah, first let me be clear about something, which is that the bias is not, if you train a deep neural network on a data set that came from some biased decision-making procedure, it's going to reflect that bias, but so will regression, and so will anything invented before regression. And this is about building predictive models, and the deep neural network is not the first predictive model. Like regression and all these things are also predictive models, and they will also convey, if regression is the right model for your task and it gives good predictions, it too will convey the same biases if you use regression to make the decision. So it's not a criticism of deep neural networks in particular, it's rather this passive prediction way of thinking about data analysis. And as to the second part of your question, if I understand correctly, is to say, can we use these statistics and machine learning methods to help identify biases in the data? I think the answer is yes. That's promising. That machine learning and statistics methods aren't just used for prediction, but as we've been talking about here, they're also used to characterize the shape of the distribution of the data, and using methods to do what's called density estimation to characterize the shape of the distribution of the data, and then interrogate that distribution to see whether or not things look biased. That's a promising avenue, absolutely. One that I'm not sure is well explored.
Just a bigger picture question. I was wondering.
Can I add one more thing?
Oh, yeah.
I wouldn't want to put anyone in jail based on that. Okay. Clear. Stakes are lower.
Could you perhaps give some examples of processes that affect our day-to-day that are informed and underlain by machine learning that we might be surprised to know are done in that way?
Yeah, I'm not sure I'm particularly an expert in that area, but I think you'd probably be best asking at this point what's not. Most of your interactions with your phone are informed by machine learning techniques or a variety of predictive technologies. And so, we all have the benefits and sometimes the failures of spam filters, which are some of the earliest applications of some of these predictive technologies. But the coupons you get when you check out at the supermarket, so I'm not sure.
And all of the advertising that you see online, those are all machine learning algorithms that have segmented the population and said, okay, people like you, we think this is who you are, and people like you have purchased these things, and so forth.
Okay. A question back here?
So it's Ron Winslow again, but so I recently bought a Tacoma pickup truck, and I constantly get more ads asking me if I want to buy a Tacoma pickup truck. So does this speak to they're only able to predict based on the past and not look at things in the future? I mean, why wouldn't they be able to know that I already did that and try to sell me something else?
I think it means you should clear the cookies in your browser. And
Well, I would ask you a question, which is I think you should consider whether you need two of them.
On that very point, there was a story that someone went to Amazon and bought a video disc of some sort, and then when they went back, the price had increased. And when they cleared their cookies, it went down. So Amazon figured, well, if you got one, you might as well have two. What kind of things do those things worry you? Do they scare you? We know about putting people in jail. We know about figuring out if you're gay and straight. What hurts you guys keeps you awake at night?
Well, I'll speak briefly to this. I think this is a very important area of research that we need to think about, which is that in the history of computer science, we've never had a time like this where the algorithms that we in computer science are developing are deployed at such massive scale and to such great effect. And so, of course, when we do that, computer scientists, policymakers, philosophers, political scientists, sociologists, we need to sit down, understand what are the effects of deploying algorithms at large scale. Yeah, this does, I wouldn't say it keeps me up at night, but I think it's an important issue. And we see it unfolding every day in a different way, things like news feeds, et cetera.
And there is a rather new area of research on this, differential privacy and basically computing research that tries to say, yield completely kind of private results, take big data sets and draw inferences from them or make predictions from them without revealing the identity of any particular user. So I do think this is an active area of research.
Yeah, I want to add one more thing. Personally, I would love to see a recommendation system that guaranteed for me that it did not store my history data on some external server. If there was a privacy-preserving recommendation system, this is something that I personally would want to use.
All right. If we don't have any other questions, thanks very much to our speakers. That was an excellent briefing, and we appreciate your time. Thank you.